In this section, we're going to explain about the Lagrange method of constraint optimization. The Lagrange multiplier method. This method is named after the mathematician Joseph Louis Lagrange, and this method is used when more than one variable is used for the optimization. Then consider the following example. Maximize z equal to a function of xy, and it is subject to g, a function of xy equal to 0, and the solution is given here. This is the objective function. Maximize z equal to, it can be minimized also, z equal to fx, f of function of x and y, and it is subject to the constraint gxy, and the method of solution is given here. The first step is create a new function. We have an objective function and constraint. That is, the first step is create a new function. For creating the new function, we have to follow this following step. First, introduce a new variable, say lambda. A new variable is introduced here, say lambda. Then multiply this constraint using this lambda. That is, lambda, find lambda into g of xy. But that is, multiply the new variable with the constraint. Here the constraint is g, a function of xy. Therefore, multiply by this constraint by lambda. That is, find lambda g xy. Multiply the constraint by the new variable and add the objective function and the new constraint. The objective function is z, a function of xy. Then add it with the new constraint, which is multiplied by the lambda. That is, find fxy plus lambda g of xy, and let it be L, a new function. It is a new function, and this new function is named as L. L equal to a function of xy. This is the objective, plus lambda g of xy. This is the constraint. This is the first function. That is to create a new function. For that, we have an objective function, either minimize or maximize. There will be a constraint. First things to do is multiply this constraint by lambda, then add it with the objective function. Then create the new function L, or whatever you can put any name as. Here it is termed as L, that equal to fx plus lambda gxy. Lambda measures the marginal change in the value of objective function resulting from 1 unit change in the value of constraint. For that purpose, we are taking this, or we introduced the lambda. That is, marginal change in the value of objective function resulting from 1 unit change in the constraint. Here L is equal to a function of xy plus lambda g, a function of xy is given. This is the new function. Then the new Lagrange function, or the new function, has 3 variables, x, y and lambda, and the maximization requires the satisfaction of the first order condition and the second order condition. Then now we want to see the first order condition and the second order condition. The first order condition is the same thing as the first order condition equal to 0. That is, take the partial derivatives of this L function with respect to x, y and lambda and set them all equal to 0. That is, find dou L by dou x equal to 0, dou L by dou y equal to 0, dou L by lambda equal to 0. Here, dou L by dou x equal to fx plus lambda gx. For that, we can write this as first order condition as fx. That is the differential of this function with respect to x. For that, we can specify it as fx plus lambda gx. And likewise, dou L by dou y equal to fy plus lambda gy. And dou L by dou lambda equal to gxy equal to 0. And for maximization and minimization, the first order condition is same. That is, take the differential of this function with respect to the variable. The second order condition is obtain the bounded Hessian determinant. That is, we need to create the matrix from the above equations. These are the 3 equations. Here we have the constraint. It is termed as gx and gy. These are the constraint, and in addition to that we need some other variable here. The bordered Hessian matrix is termed as 0, gx, gy. Here also gx and gy. Here lx and ly, lyx and lyy. These are given. The other elements in the matrix are this. This lxx and lxy are the coefficient of the x in the first equation, and the coefficient of y in the first equation is termed as lxx and lyy. Here lxx and lxy. The second element is lyx and lyy. It is corresponding to the second equation, lxy and lyy. Create a matrix from this, and for maximization the determinant should be greater than 0 of this function, or this matrix should be greater than 0, and for minimization the determinant of this function should be less than 0. Let us take another example. Maximize set a function of xy subject to the constraint C. Another example is given here. Maximize set a function of xy subject to C equal to p1x minus p2y. The constraints can be expressed as C minus p1x minus p2y equal to 0. Step 1 is create a new function by adding the objective function constraint multiplied by lambda. That is, multiply this function. The constraint can be expressed in the form of C minus. The constraints can be expressed as C minus p1x minus p2y equal to 0. Then multiply this by lambda. Then add it with the objective function. Then we will get the new function L equal to fxy xy plus lambda C minus p1x minus p2y. This is the new function. Then the conditions are take the first order differential or the first order condition, or they take the partial differential of this function with respect to, we have three variables x, y and lambda. That is dou L by dou x equal to fx minus lambda p1 equal to 0, dou L by dou y equal to fy minus lambda p2 equal to 0, dou L by dou lambda equal to c minus p1x minus p2y equal to 0. Then the second order condition is that the bordered Hessian, like this, the bordered Hessian matrix is constructed as this gx and gy are the values of the constraints. Lxy is the coefficient of this x variable, Lyy is the coefficient of this y variable. Then Lxy is the value of the y variable in the first equation, Lyx is the value of x variable in the second equation. If this is greater than 0, the condition or the maximization condition is satisfied. If the determinant of this bordered Hessian is greater than 0, the maximization conditions are satisfied. Let us take an example to explain the above explanation. The objective function given is y equal to x1 x2 plus 2x1, and it is subject to x1 plus 2x2 equal to 0. Here this constraint can be written as 20 minus x1 minus 2x2 equal to 0. This is given here, and multiply it with lambda. This is the first condition step. Then create a new function L equal to x1 x2 plus 2x1. This is the objective function plus lambda 20 minus x1 minus 2x2. We have created new function. Then take the first order partial derivative. We have three variables x1, x2 and lambda. Therefore, there will be three equations. Dou L by dou x1 equal to 0. Dou L by dou x1 equal to, that is, differentiate this function with respect to x1. Then it will give x2, x1, x2 means differential of x1 is 1. Therefore, x2 plus here 2x1. Differential of 2x1 is 2 minus this lambda. We need to multiply it with all this function, 20 lambda, x1 lambda, 22 x2 lambda. Then we will get 20 lambda. Here there is no x1, it is 0. Lambda x1 means differential of x1 is 1, therefore lambda minus 2 lambda x2 is the third component. Here there is no x1, it is equal to 0. Therefore differential of this equation with respect to x1 equal to x1 plus 2 minus lambda equal to 0. Let it be the third equation. And likewise dou L by dou x2 equal to 0. The differential of x1 x2 is given as x1. Here there is no x2, therefore it is 0. Then differential of this one will give, this is equal, here there is no x2 is 0. Here lambda 2x2. Lambda 2x2 will give the differential of lambda minus 2. Lambda x2 is minus 2 lambda. This is equal to 0. Then differential of dou L by dou lambda, that is take the differential of this function with respect to lambda. Here there is no lambda, therefore it is 0. Here we have one equation. The differential of this equation where this variables will give 20 minus x1 minus 2x2 equal to 0. That is, this equation is 20 lambda minus lambda x1 minus 2 lambda x2. If we differentiate this function with respect to lambda, we will get 20 minus x1 minus 2x2 equal to 0. These are the three equations. Now from equation 3, x2 plus 2 equal to lambda. From equation 4, x1 by 2 equal to lambda. x2 plus, that is x2 plus 2 equal to x1 by 2 equal to lambda. From this we can say that x1 equal to 2 into x2 plus 2, that equal to x1 equal to 2x2 plus 4, or x1 minus 2x2 equal to 4. This is the equation number 4. Add equation 2. This is equation 2, that is x1 plus 2 x2 equal to 20, and this equation x1 minus 2 x2 equal to 4, that is x1 plus 2 x2 equal to 20 plus x1 minus 2 x2 equal to 4. This will give 2x1 equal to 24, that is x1 equal to 12, and substitute this into equation, that is x1 minus 2x2 equal to 4, that is 12 minus 2x2 equal to 4, or 2x2 equal to 8, or x2 equal to 4. Therefore we got the value for x1 and x2, x1 equal to 12 and x2 equal to 4. Now we want to check the second order condition. The second order bordered Hessian matrix is that we construct the bordered Hessian matrix 0, g1, g2. These are the constraints. These are the coefficients of the other variables x and y in our cases. These three, we have given the three equations. The three equations are given again here. That is L1 equal to x2 plus 2 minus lambda. This is the third. L2 is the x1 minus 2 lambda equal to 0. Lambda equal to 20 minus x1 minus x2 equal to 0. Here in the first equation there is no x1, therefore L11 equal to 0. And here L12, the coefficient of x2 is 1, therefore L12 equal to 0. Here G1, the coefficient of this lambda equal to 1. And second equation is L2. Here the coefficient of x1 is 1, therefore L21 equal to 1, and there is no x2, therefore L22 equal to 0, and coefficient of this lambda equal to 2. Everything is the absolute value. The signs are not considered here. Therefore we can construct the coefficient as 0, 1, 2, 1, 2, 0, 0, 1, 1. Then find the determinant. Determinant can be found as 0 into this row and column is removed. The determinant, the remaining portion is 0 into 0 into 0 minus 0. 1 minus 1 into 1, that is 0 into 0 into 0 minus 1 into 1, or 0 into 0 0 minus 1 into 1 is 1, that is 0 into 1. Likewise minus alternative sign, minus 1 into this row, this column and row is removed, then the remaining elements are 1 1 2 0. Then take the product, 1 into 0 minus 2 into 1. that is minus 1 into 0 minus 2 plus alternative sign. Here the sign will be plus 2. This is the third element. To remove this row and column, the remaining elements are 1 0 2 1. That is plus 2. 1 into 1 is 1 minus 2 into 0 is 0. That is we will get 0. Here this is 0, that is multiplied with 0 plus 1 minus 1 into 0 is 0 minus 1 into minus 2 is 2. That is 0 plus 2. Here 2 into 1 is 2. 2 into 0 is 0. Therefore 2. 0 plus 2 plus 2 equal to 4. This is determinant of this matrix. Since it is greater than 0, the second order conditions was also satisfied. The given function will maximize when x1 equal to 12 and x2 equal to 4 and the maximum value equal to 72. This is the method of constraint optimization using the Lagrange method.